Hello, everybody. My name is Daniel Petranek. I am a software developer. I'm currently working on an immutable graph database that's written in Clojure called Flurry. Flurry is really cool for a lot of really cool reasons. Um, and today I'm going to be talking about, well, this is the title talk that I submitted way back before I knew what I was going to talk about. This is mutable databases will set your distributed system free. And it's true. But I think this is a better title. Uh, Databases, where we are, how we got here, and why immutable is where we're going. Because in the course of trying to talk about distributed systems, I had to figure out how we got here. And it turns out that that's interesting enough that it's worth sharing with everybody. So, yeah. I started learning Clojure in 2013, which is like more than 10 years ago now. And I'm still impressed with how great immutability is. Um, if you're new to Clojure, you may be surprised about how little mutation you actually need to make a good system. There's a 2022 survey of all Clojure GitHub repos. Um, and in that survey, they found that the average number of mutable vars in a repo was less than 2, and that a full 63% had none at all. It really is, you don't need as much state as perhaps you might expect if you're not accustomed to Clojure. And there are caveats to this. They were just doing static analysis, and there's always ways to dig into the JVM and mutate, but that kind of reflects my experience. You just don't need mutation. And I'm going to go out on a limb and make a strong statement that I don't think you need to mutate at all unless you have a performance problem. Like the only reason that we need mutation is because we have physical machines that we need to run our programs on. Uh, and sometimes they're not as beefy as we want them to be. So we could write whole programs that are wonderful to work with. Clojure is a dream. Like you can def out your values. You've got pure functions that you can play with in your REPL connected editor. You've got structural editing. That doesn't have much to do with immutability, but it's great. It makes you feel like a wizard. And just in general, working with systems that utilize immutability is like a joyful process. I enjoy the time I spend in my REPL. And you can do this, I would say the typical program that people work with in Clojure, maybe Clojure's bread and butter is kind of how I think about it, is you've got an HTTP server getting HTTP requests. They come in, you're going to authenticate them, authorize them, validate them, maybe transform them and store them in a database. And this, from request all the way to database, can be this beautiful, pure system. But there's a fly in the ointment in that we're usually writing to a mutable database. We just push the mutability to the edges. And this sucks because all of the stuff that we enjoy about working with in the guts of our Clojure program are now gone because I've got to set up a database. I've got to run migrations. I've got to massage the data into the state that I care about. If I'm running tests, I need to make sure it's torn down correctly. And so by pushing, like, we're just delegating this gunk to somebody else. And there are ways that we can write code to preserve the pureness for longer, but it's hard. And so we've got all these mutable databases. Why do we need to do this? And sorry, I just need to backtrack for a second because mutable databases ruin everything. At every step through this process, if I'm authenticating, I need to query if I know this user. And databases are not referentially transparent. If I run the same query at a different time, I'm going to get a different result, probably. Maybe I won't, but I can't guarantee that. So I have to keep checking. Authorization, I have to check to see what permissions this user has once I've authenticated them. Validation, usually like, I need to check if this data is unique. That means going to a database and checking and getting back a different answer every time. And if I'm doing data synthesis, which is where useful stuff happens, I might be talking to multiple databases. I may have like prepare to shutter integrations. Like, and that sucks. You got to work with somebody else's data now. Who knows what's going to happen? They might be down, for goodness sake. You might not have access to that. And so we're stuck in this pit of mutability, and we're sad about it. And that's just where we are. Why use mutable databases? Can any of you name an immutable database that's not datomic and is not XTDV? Look outside, like they exist, but they're like, you're using MySQL, you're using Postgres, you're using MongoDB, God bless you. Like you're using Cassandra maybe. And all these different database systems are destroying data on every single update. If immutability is such a good idea, where are the immutable databases? It's an accident of history, is what I'd like to say. It's not an accident. We're going to take a step back and talk about what is a database. And I'm not going to do the Rich Hickey thing where I look it up in a dictionary. I'm going to make up a definition because this is how I think about it. A database is a system for organizing inputs for efficient retrieval. Now, I've got a couple of kids that they're the first grandkids on both sides of the family. And they've got a host of uncles and aunts. And that means every special occasion we get a few Lego sets. And it has turned out to be my job when we're assembling these Lego sets to carefully organize all the pieces by color and then by shape. And while I'm doing this, I'm explaining that, hey, I'm actually making a database for you. And look how much faster your queries are running now that I've run my indexing job. And the kids will see, yes, thank you, Dad, but you don't have to say this every single time we do it. And I insist that, no, I do. This is sort of a database. Libraries are databases. You've got books, physical books, and they're, well, not just books. First, you sort by format. You've got your audio books, you've got your regular books. That's it. And then you sort by genre or topic, and then you sort by author's last name. And it makes it really easy to find a book about anything you're interested in as long as you know vaguely what it's about. One of the oldest and most popular databases in the world is the accountant's ledger. Double entry accounting goes back, according to my quick Wikipedia check, to maybe AD 70. Pliny the Elder mentions this in one of his histories, which if you squint at, you could say, yeah, that's double entry accounting. But it's a really good idea because by tracking an immutable ledger of transactions, you can ensure you don't lose money, which turns out to be an important problem that a lot of people have. But we're software engineers, or maybe we're not, but I'm here talking about computers. And so what we really care about is computerized databases. And so I'm going to talk about a very simple database. It's just a key value store. It's append only because appending to the end of a file is just about the cheapest, fastest way to store data. And in this database, you just append a key and a value to the end of a file. And in order to look something up, you just scan to find the last occurrence of the key that you care about. So my name is Daniel. I live in Madison, I like mangoes, and have I viewed an eclipse? No. But yes, now I have, and so I just append a new version of that uh, key down at the bottom. And in order to find this, I just scan. And when I get to viewed eclipse, I'm going to skip this one and go to here. This is an awful database because in order to know that you've got the last value of a key, the last entry that a key exists, you have to scan the entire file every single time. You don't know that the next key might be the one you're looking for. So you've got to do the whole thing. So as this database gets bigger, performance is garbage. This is barely a database. I would say it's not a database because it's not structured for efficient retrieval. So let's add an index where we just have a map of each key to the line of its last entry. Now it's roaring fast. I could jump to an offset and just read from there. That's really fast. You can do this with command line utilities, and this would work. I wouldn't do that, but you could. The point of this, though, is that databases are about trade-offs. You spend a little bit more time when you're writing the data to get time back when you're retrieving the data. And what matters is what retrieval patterns you care about. If I'm looking for a book in the library and all I know is that its cover is yellow, I'm just out of luck because it's not indexed for that pattern. I'm going to have to go through and pull every single book and check, does this one have a yellow cover? Nope, next one. And there's a lot of ways that there's different retrieval patterns, but like you kind of need to pick a few. Because the number of retrieval patterns you can support has a cost. It gets expensive based on your constraints. And let's talk about constraints. This is a very loose timeline of databases. In the 1960s even, you've got mumps, which I'm not going to elaborate on. If you don't know about mumps, be glad. um, you've got Edgar Codd wrote his relational algebra paper in 1970. You get Ingress and Oracle, early relational databases. In the 1980s, you get post-Ingress, DB2, Microsoft SQL Server. The 1990s, you get MySQL and finally PostgreSQL. In the 2000s, we start seeing some non-relational databases like Neo4j, MongoDB, and Cassandra. And all of these databases, and these are kind of the big ones. Like if you don't have an opinion about a database, you're probably going to use something near this list, probably on this list. Probably you're going to use MySQL or Postgres, right? And these all were developed and researched during a time of a very specific constraint. This is the very first 5.25-inch hard drive. This one. It came out in 1980. It cost $1,500 at the time, which was about $5,500 in today's dollars. And it could store 5 megabytes of data, which is not much. And so all of these different databases had to, like, they could support one retrieval pattern, maybe a few more if they kind of fudged it, but they didn't have the budget to sort of spend on support on flexibility. It's not that they didn't know that they were making this trade-off. This is a paper from 1980 by George Copeland. And he writes, what if mass storage were free? And this is the paper. It's very short. I highly recommend reading it. It's very readable and succinct. A fun read, if you will. But I'm just going to read this segment. He says, It is argued that free mass storage would free database systems from the limitations and problems caused by conventional deletion techniques. A non-deletion strategy would significantly simplify database systems and their operation, as well as increase their functionality and availability. And this whole paper is about, like, we have to jump through so many hoops in order to use our precious disk space efficiently. And it's funny, he writes this paper and he's like, for 30 years, hardware has been getting better. And now we're like more than that amount of time in the future. And it has gotten cheaper. It hasn't gotten free, but this is 1980, and this is mass storage. And we come down to less than $100 per terabyte from 100 million per terabyte in 1980. So it hasn't gotten free, but it has dropped 4 orders of magnitude, which may be as good as. And so you see, this is a Google Ngrams search, which I don't think is very scientific, but I just wanted to show the trend line. It's not until very recently that even the mutable databases became feasible. I'm going to talk more about that later. So databases are about trade-offs, and you've got retrieval patterns that you care about, and then you've got the hardware constraints that can serve them. I'm going to take a little detour here, and we're going to talk about big data, because there's a discovery in the 2010s of a new source of data. It was very exciting. It wasn't a secret to developers. We knew about it. We created it. Application logs. We've been writing this since the beginning of time, print log debugging, to understand how our system is behaving in action. And I don't know how this actually happened, but I imagine that it went something like this. There was a developer and a business analyst, and they were talking about some bug, and the developer goes, oh, let me just quick check what time this user logged in. And the analyst was like, what? I helped design this system. I know that we're not storing login times in the database, so what are you talking about? And he's like, oh, well, it's just in the logs. Let me just quick check. Oh, is it 5 o'clock? Yeah, okay, that helps. And the business analyst goes, well, can you do that for any user? And the developer's like, yeah, like, who do you want me to check? And the analyst goes, can you tell me when people logged in on Christmas Eve? And the developer goes, oh no, we delete these every 30 days. And the analyst goes down the hall into the conference room, crouches down, pulls their hair, and goes, "Argh!" Comes back and says, could we keep these? And the developer's like, I guess, but it takes up a lot of disk space. And the analyst goes, well, how much are we talking here? He's like, well, we might need like a few extra terabytes. And the analyst goes, well, how much would that cost? And he goes, like maybe $200. The analyst goes back to the conference room and goes, let's save that data. Now we've got a whole bunch of new problems. This is the useful data. This is the data that tells us all about intent. It tells us how our service is being used. But there's a lot of it. We generate it constantly. And now it has to live on more than one machine, which means we need to start solving some hard problems. This is a book I brought along as a prop. I highly recommend everybody read this. This is one of the most influential books that I've read in my tech career, Designing Data-Intensive Applications by Martin Kleppman. And it's a very succinct description of everything that can go wrong once you have more than one machine. This is about as small as you could make it. And this is just a part of it. Now you've got to partition your data across different machines. And when you partition it, now you need to figure out how you're going to distribute that load. You need backups. And so now you've got to figure out how to safely replicate the data. There's a lot of different ways to do that. buckets of ink have been spilled over that, as well as actual blood from developers pulling their hair out. You've got to decide between consistency and availability when your network partitions, which is a funny way of saying somebody cuts the wire and all of a sudden the machine disappears. You've got to figure out queues, transaction isolation, back pressure, microservices start like reproducing like rabbits. Then you need service discovery. There's monitoring and observability. These are hard problems, and we have to deal with them for the first time. I want to caveat that by saying in computer science, hard problems are always discovered and probably solved 10 years before you encounter them. But we're not reading the papers, so we don't know about that. Sometimes 20 or 30 years. It can be really humbling to look back and say, oh, that's how you do it. And my degree is actually in economics, and economics is the study of allocation of scarce resources, maybe the efficient allocation of scarce resources. And one of the very useful things that economists have come up with is they've got graphs. They didn't come up with graphs, but this is a very interesting type of graph where you measure this is a production possibilities frontier. And if you are an economist, you will know that this line should be a curve, but I could not figure out how to make curves in this software, so we're getting a line. But the point is, you make a trade-off. You can be anywhere on this line. Like right here, we can support as many retrieval patterns as we'd like, but it's so slow that it never finishes. It doesn't work. Or here, it could be super fast, but we only support one retrieval pattern. And for most of history, we've been clustered very close to this edge because everybody needs some very basic functionality out of their database. But now we've got this big data. We've got a whole host of new questions we want to ask from it. We've got way more retrieval patterns that we care about. Fortunately, we also have a lot more speed at our command, which means we've got a whole bunch of space on this possibilities frontier that we can explore. And there's been, in the last 10 years, not a literal, a figurative explosion out of databases that are starting to explore this frontier. And again, it's all get back to the constraints and the trade-offs. That's a lot of different spaces. That's really cool. That's exciting. This is thrilling. We're at a Cambrian epic of database management systems. I love it. And so one of those types of trade-offs can be found in immutable databases. Immutable databases I really like because I really like immutability. It's been proved to me that that's a very useful thing to have in my program design. I would love to be able to access it in my system. So I'm going to talk about immutable databases. I'm going to talk about a specific one because I know one in particular quite well. But the general principles here apply. I'm going to try to not get too much into Flurry-specific internals. These techniques for building an immutable database would work. You could take slightly different implementation choices and get slightly different places. But I want you to understand. So first, I'm going to talk about graphs. Because everything can be a graph. I'm not sure if that's actually true, but I think it's true. I think everything can be a graph. It's a very general data structure. You've got vertexes or nodes and edges, and they're connected. In a graph, you don't have to have directed edges. This one does have directed edges because they've got arrows, because that's what I chose when I made that graphic. And one way that you can notate a graph is to use triples. In this case, this is the traditional nomenclature, subject, predicate, object, according to some traditions. Daniel loves Clojure. I'm the subject. This is the predicate. This is the object. I think these are better names. These are newer names, at least. Entity, Daniel. Attribute, loves. Value, Clojure. I should have said immutability for this talk. But you could represent JSON as triples. And you can see here how we map the IDs to the subjects. And then all the keys become predicates, and all the values become values. And this one, employer, is a special sort of value. It's a reference to this. You can see the link there. And so you can read these triples in and instantiate in memory a graph that looks just like that. And you can traverse it in a variety of different ways. I'm just going to mention this briefly. RDF is a name for a sort of triple notation that I think is, a lot of people use that sort of notation, and there's a lot of technologies that are built on that notation. It's just a convention. Graphs are graphs, but conventions make happy neighbors. So if you're interested in any of those, I'd like to talk more about them later, but I'm not going to say much more. So if you're building an immutable database, first thing we can do is we can take some data. Barry's favorite food is chocolate and has friends Emily, who likes mangoes, and Fred, who likes rhubarb pie. And we turn it into triples. This is easy. And now we have an update. We're going to say, for number 2, Emily, we're going to say she likes graham crackers as her favorite food, right here. Boop. In order to do this, we need to add a temporal dimension to our triples. It's just a fancy way of saying we need to know at what point in time this triple, another way of saying a triple is a fact, when is this fact true? And so now we see that Emily likes mangoes and graham crackers. There's mangoes, graham crackers. Way to go, Emily. Those are delicious. But what if we wanted to say she changed it? And she no longer likes mangoes. She only likes graham crackers. Well, in order to support that, we need a new dimension to our triples, and this is the assert. This is validness. This is whether it's a fact or not at this point in time. And so we could say here, favorite food mangoes at 2, that's no longer a fact. We've retracted that fact. It's still there. We haven't lost it. We haven't destroyed it like we would in a immutable database, but it's no longer true. And now her favorite food is just graham crackers. And when we query it out, we can see, bam. We go through and we say, if we're looking for Emily, we just say, we're going to find the latest true fact for each predicate, for each attribute. That's simple. That's easy. And then in order to find things, we just use pattern matching. You may be familiar with SQL. If you like SQL, cool. This is really easy because you're literally just looking at the shape of your data. These are triples. The question mark means a variable. I'm gonna match any subject can be assigned to person, and any person who has a friend, we're gonna match that value as a friend. And we care about a friend whose favorite food is mangoes. And then we want the name of the person who has a friend whose favorite food is mangoes. And so this is a query that will just give us the name of all of our friends who have friends who like mangoes. So maybe they can introduce me to them and we can have a mango party. That's easy. That's simple. And now if we want to persist this, because right now we just have a list of triples, we want to put this on disk. Take a leaf out of Clojure's notebook and just use persistent immutable data structures. You've got a tree, And we just keep track. This is just a B plus tree. We just keep track of what the leftmost triple is, what the rightmost is, and all the data just lives in a set, a sorted set in the leaves of the tree. And when we update, we generate some new versions of the leaves. We don't change any of the existing data. We just create pointers back to the stuff that hasn't changed. We're sharing that structure. Voila. Voila. It works. It's persistent. It's immutable. Nobody has to have their data changed from underneath them. But it requires more space. So while we've got these triples, these extended triples, I guess I would say, you sort them in these different indexes. In the spot index, you sort them by subject. In the post index, you sort them by predicate. In the TSPO index, you sort them by the transaction time. And now we can ask questions like, what was Emily's favorite food at time 1 or last Monday? And we can answer that really, really efficiently. But the cost of that is that each of these indexes duplicates all of our triples. So you see how quickly adding dimensions to our indexes, if we want to be able to access them efficiently, we need a lot of indexes, and it takes up a lot more disk space. Thank goodness things are cheaper, otherwise this wouldn't quite work, but things are pretty cheap. And I think a lot of the times this is worth it. So now we can have immutability in the large as opposed to immutability in the small, where we're just working with our program. Copeland was right in 1980. He was right. We get more functionality. We can ask interesting questions like about time. We can see how things change. And it's much less complex. I don't know if anybody has ever looked at the internals of a relational database. There is a lot of complexity there. MySQL, I think, by default, has some serious transaction isolation issues out of the box because it's very hard to get it right. They have this very expensive multi-version concurrency control system that tries to make sure that data that's being updated isn't being read by anybody else. And so you've got row level locking. It gets really complex and it's very difficult to reason about. It's expensive and difficult to change. And then people start relying on broken behavior, so you can't just fix it. It's a tough problem. When you can simplify the most important aspect of your system, and I think the database really is the heart of a system, you could breathe much more easily. Everything becomes easier. When time is a first-class concept, you can do really useful things. You can have time travel. You can see how things change over time. You can do bitemporality. So a temporal database allows you to ask the question, what did things look like as of this time? A bitemporal database makes a distinction between when is this fact true and when was this fact known, which you may wrinkle your forehead about. And it can be kind of difficult to get your head around. But I think the easiest way to explain it is if you have a bitemporal database, you can ask questions like, when did this change? Whereas if in a temporal database, you have to actually go through and look at every single change through history. And you can efficiently look at the whole history, but you can't query time itself. You can't say, when did it change from this to that? Or and you could go beyond bitemporality. If you've got a big brain, uh, I don't quite get this yet, but I know of at least one tritemporal database. I know of nobody who's gone beyond, but that's an option. So you had validness, you had transaction time, and you had oh, I don't, it was like a really specific, I think it was like an evidence management, and they had something like trustworthy. I don't like, I'm just making stuff up now. Who knows? I know it exists, and that's all I'm willing to go out and commit to. Um, but with an immutable database, you get a lot of functionality out of the box that right now, if you want, is an engineering project. They're like, people want this sort of audit log, and they've got mutable databases, and they've figured out how to make it work. It's a lot of work, and if you screw it up, you lose important stuff. I know there's at least one project that parses Postgres's write-ahead log, which is an internal implementation detail, in order to extract sort of this event log of changes over time so that they can do temporality. But you would never choose to do that if you were starting from scratch. You wouldn't say, let's put it all into a system that's going to destroy historical data, and then we'll just like trick it into giving us the history. No, you'd use it where you'd use a system where that's first class. And you could build event source systems. Now, the databases that we use today, the mutable databases, have been around for 50 years. The relational model is pretty well understood. And it's still early days for event sourced systems. So people are still trying to figure this out. But the places that do figure it out are making really cool stuff with it. And it's a lot easier with immutability. So now I'm going to talk. How am I doing on time? Okay. All right. This is where I get really excited because the future is wild. Everybody's exploring the new possibilities of cheap hardware and lots of data. They're asking all sorts of new questions. They're figuring, there are so many new databases in the last 10 years, even in the last 5 years. They're popping up all over the place. And I'm especially interested in graph databases. Um, you saw graphs. Relational databases, which you may be used to, don't compose very well. Every single relational database, every relation or table is its own kind of special snowflake schema. And so in order to connect between them, you have to understand how to connect, how to parse and understand, how to ingest this data, and how to join it with other data. Graphs compose trivially. It's all triples. It's the same API no matter whose database you're querying. If you use the same identifiers for semantic identities for your entities, you can join across databases trivially. And I hate it when people use the word trivial when talking about computer problems. Um, so maybe not trivially, but trivially compared to the hoops you've got to jump through today. And I don't know about you guys, but I often feel in today's day and age that I don't have very much control over my data, that I'm a digital serf living on the manner of these large, incomprehensibly titanic entities that do a really bad job of managing it. Yeah, oh, it works real well for them, apparently. But I've been in like half dozen different data breaches that I know of. Um, and that really like, if you want to freak yourself out sometime, uh, read about East Germany, and the East German secret police in particular. This was before databases existed, and they managed to exert like a truly terrifying amount of control over their people uh, with just files in folders. And I'm a little terrified of a future with all this data running around because of history. Bad things happen. Um, and so I want to build a future where users can own their data and not have to share it with people. I get excited about graphs because they can compose really well. And so you can build ethical systems that don't necessarily just vacuum up everything. It doesn't all have to be co-located in one giant castle. Uh, there's a lot of different ways to do this. Once you get into event sourcing, every index is just a materialized view, like a concrete. We're going to favor some access patterns, but if you just have the log of the transactions over time, you can materialize it in any sort of index that you want to support. It doesn't have to be that sort of those different triple indexes. You could put it into a vector database and make your own private learning language model. I think that's what that is. You can do your own analysis on it. You can bring the computation to your data instead of sending your data to the computation. Um, I think that's really exciting. Uh, I don't know. There's a lot of really cool stuff that's possible now that constraints have been lowered so much. And now we've got so much data. We can ask so many interesting questions. Um, so that's basically everything I've got to say. Here's some references. Uh, but this is the cool stuff. And I kind of want to work on these problems for a very long time, because even working on one database, every single time we have to make an implementation decision, I go, wow, if we did it this other way, we could do this other things. And so you've got to sort of prioritize what it is. In the conclusion of this book, Designing Data Intensive Applications, which was written in like 2015, I think. Who knows? 2017. He talks about turning these databases inside out and having different components and just gluing them together a la carte in the way that work for you. Build your own database. And we're starting to see that now 5.5, 6 years later. And this is literally just the beginning. In 50 years, the databases that we're coming up with now are going to reach the sort of stability and reliability. I shouldn't say 50, 30 years from now. Next year. uh, but like, one of the reasons we keep going to the established technologies is because they're established. We don't want to risk our data with these newfangled things. We don't want to learn these new system architectures. It hurts our brains, uh, because distributed systems do hurt your brain. Like, they're hard problems, and I don't want to say that this is a panacea that's going to make everything easy, but it'll make it doable. And you'll be able to look at your system and understand it in a way that's very difficult now. Uh, and I think that's exciting. And let's build it all with Clojure, with virtual threads. Yeah. So, all right, that's it. Does anybody have any questions?